Hello, everyone. Welcome back to another presentation from our forum, SAE Brazil Aero Design 2021. It's again a pleasure to be a part of it and help spreading the knowledge and connecting students with successful professionals worldwide. For those who don't know me, my name is Diego Moraes. I am an embedded software engineer. I'm a member of the technical committee responsible for electrical project and embedded systems. Today, I'll be the moderator for the next presentation, which is Aerospace Education and Innovation in the Digital Age. Before we start, I'd like to just say a few remarks. The quality of YouTube video is normally set to low by default. So I advise you just to set it to a higher quality in order to be able to better follow the slides. Also, in case we have any streaming issues during the presentation, please don't panic. We will try to fix as soon as possible or find a workaround and we'll let you know. We also encourage you to send us questions during the presentation. You can send the questions through Slido. Someone from the organization will send the number in the chat soon in YouTube. Please send the questions using Slido only because we don't look at the chat. We don't always look at the chat in YouTube. And yeah, you can also upvote the questions you see there and you like more, you want to be answered. And yeah, now I invite our speaker, Professor Karen Willcox. I believe some of you might already know who she is, but I'll present a short version of her bio just for those who don't. Yeah, Karen Willcox is a director of the Oden Institute for Computational Engineering and Sciences, Associate Vice President for Research and Professor of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin. Prior to joining the Oden Institute in 2018, she spent 17 years as a professor at the Massachusetts Institute of Technology, where she served as Professor of Aeronautics and Astronautics, the founding co-director of the MIT Center for Computational Engineering, and the associate head of the MIT Department of Aeronautics and Astronautics. She's also an external professor at the Santa Fe Institute. She holds a Bachelor of Engineering degree from the University of Auckland, New Zealand, and master's and PhD degrees from MIT. Prior to becoming a professor at MIT, she worked at Boeing Phantom Works with the Blended Wing Body Aircraft Design Group. She currently has funded projects supported by the U.S. Air Force Office of Scientific Research, Air Force Research Laboratory, ARPA-E, Department of Energy, Lockheed Martin, NASA, and Sandia National Laboratories. She currently leads several multi-institution research teams. And in addition, she's active in education innovation, which is, by the way, the focus of her presentation today. Yeah, so now that you know a bit more about her, it's time for me to stop talking and let her start her presentation. So, Karen, you have the floor.
All right, thank you very much, Diego, for the nice introduction. It's really great to be with you all virtually today. And I should mention that I'm currently in New Zealand. I'm in a quarantine hotel run by the government because I just arrived in New Zealand for a couple of days ago. So I'm sure this must be the first presentation ever given from quarantine in New Zealand to Brazil on aerospace education. So hopefully all will go well. All right. So as Diego said, I'm going to share a few thoughts today about aerospace education and just more generally the future of aerospace. I know it's been a difficult year and it continues to be a difficult time. And I know it's a difficult time, especially for those of you in Brazil. So I think it's good to take some time to think about the exciting parts of our world and to think about the future and some of the exciting things that we as aerospace engineers have to look forward to. So go next slide, please. So I'm going to touch on three things today. I wanted to start off by framing my comments by thinking about the convergence of big data and big models. This is a topic that I'm sure is on many people's minds. And in particular, I'll talk a little about the idea of a digital twin and how that leads to multidisciplinary challenges in our future aerospace systems. Then I'll use that framing to talk a little bit about aerospace education and think about what does it mean to be an aerospace engineer in the coming decades. And then I'll just close with a few thoughts about the future. Next slide, please. So I wanted to start off by saying something that I firmly believe, and I hope that all the students that are listening today also feel this way, that really there has never been a more exciting time to be an aerospace engineer. I think aerospace engineering has always been the coolest of all engineering professions. Right now it's especially exciting. And it's especially exciting because there's just so much going on. So to think that all of us are going to see humans walk on the moon again in our careers, in our lifetimes, and we're going to see the first woman walk on the moon. We're going to see the first person of color walk on the moon. We may see people from nations other than the US walk on the moon. I mean, that alone is incredible, because not only will we see it, many of us in the profession will play a role in some way in making that happen. Second, we're just seeing incredible things with autonomous and robotic exploration of our solar system. And there are so many examples here, but again, just this past week, the things that we've seen from NASA and the rovers on Mars. Again, just incredibly exciting. And again, I'm sure that many of you can see the things that you're learning in your classes and the technologies you're exploring in your design work feeding into what's going on both in Aero and Astro up there on Mars. And then third, we're seeing so much sort of growth and innovation in the area of autonomy, especially as it impacts urban mobility. So again, in our lifetimes, I expect that we're going to see autonomous vehicles playing a big role in cargo delivery. And, again, as we think about the pandemic and think about the fact that, at least for me living in Texas, I've been trapped in my house for a year, reliant on a global supply chain, being able to pick up my phone and push a button and have Amazon deliver everything I need to my door. And of course, aerospace plays a huge role in all of that, in that global supply chain. But thinking about a future where autonomous vehicles are making that global supply chain more efficient, more resilient, with less environmental impact. And then, maybe even further into the future, we think about autonomous vehicles carrying people and making transportation around urban or even rural areas easier. So again, incredibly exciting, and I could probably fill up the whole hour just talking about all the incredible things that we as aerospace engineers might help happen and see impact our society in the coming decades. So next slide, but I'm not going to fill up the whole hour with that. I want to focus in on maybe one idea that I think is particularly exciting, and that's the idea of a digital twin. So if we now think about that framing, think about all those exciting futures, or presents and futures that I just talked about, and ask the question, why now? What is it that's really enabling all of these things? And a big part of it is the technologies. So incredible advances in technologies from materials to propulsion and everything in between, but especially a big advance over the past decades in sensing technologies. The fact that we have now sensors on our systems and that we're able to collect data about our systems like never before. So technologies, and especially sensing technologies, has been a big player. Going along with that are the algorithms. So the underlying mathematical algorithms and then the computational implementation of those algorithms that mean that we can analyze systems at a fidelity and scale like never before. So I'm sure Kim Martins earlier today talked about some of his incredible work in design that has very powerful algorithms that sit under it. And then, of course, the powerful algorithms in machine learning and data science that, again, let us analyze and draw insights from data at a scale never before. And then the third piece of it is the computing power, which the algorithms is one part of it, but the computing power that, again, lets us start to analyze and design our systems at a really meaningful scale. And that includes the high-performance computing power that we have on the ground, particularly in the design phase, but it also includes the computing power that we're starting to have on board our vehicles so that we can do onboard or real-time computing. And of course, that plays a huge role in enabling autonomy. So really those three things, the technologies, the algorithms, and the computing power, and the fact that they've all advanced and are now coming together in a way that just enables incredible innovation in the way we conceive, design, build, and operate our aerospace systems. Go to the next slide, please. So one concept that I think really encapsulates that beautifully is the idea of a digital twin. So you can see a definition here on this slide. This is a definition that was put together by AIAA, the American Institute of Aeronautics and Astronautics, through a sort of community process. So a digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of an individual or a unique physical asset, is dynamically updated with data from its physical twin throughout its life cycle, and informs decisions that realize value. So I like this definition because I think it helps us understand what is a digital twin and how is it different to the modeling and simulation that we've been doing for many years. And so I'm going to pull out three things from that definition. The first is that the digital twin is tied to an individual or a unique physical asset. So it's not a generic model of one of the Embraer aircraft. It's a model of one particular aircraft, and there's one digital twin for every aircraft that is being manufactured and operated. So it's tagged to an individual. Second is that it's not a static model. It's not a model that you create and then you're done. It's a model that is living, that's dynamically updated with data and is going to follow that unique asset through its life cycle. And then third is that the digital twin brings modeling and simulation and really wraps it around with the idea of making decisions that realize value. Go to the next slide, please. So I find actually the history of digital twins really interesting. And if you haven't read it, there's a very nice blog post from someone at Siemens that talks about the history of digital twins. The term digital twin was coined about a decade ago by in a NASA report. But the idea is much older. And many people point to the Apollo program as being the place where digital twins were first put into practice. And so back in the Apollo program, when NASA were launching Apollo spacecraft, they were also keeping simulators on the ground in Houston and using the simulators to kind of model and be a digital twin that tracks the physical twin as it's on its mission. And this came to the forefront. This became very relevant and very useful during the Apollo 13 crisis. And maybe many of you have seen the Apollo 13 movie, and so you know the story. But basically when the spacecraft was damaged, so the spacecraft is now crippled up in space, NASA were able to take data from that crippled spacecraft, feed that data into the simulator on the ground. So now they have this dynamic updating of the models on the ground, and then use this dynamically updated simulator to run the analyses and run the scenarios to play the what ifs so that they could plan the strategies that ultimately brought the astronauts back safely. So that's in 1970. That's 50 years ago, an example of digital twins and showing just how powerful it is to have models talking with data and being integrated and again being used to drive decisions. Next slide, please. So that's one example, and I'm going to give you a few more. But again, if you imagine a future where every engineering product, every aerospace system that we build comes off the manufacturing line and comes off with its own digital twin, and thinking about the big decisions, the incredible value that could bring. Next slide, please. So I'm going to give you a couple of examples and things that I've worked on. So one is, I think digital twins are a essential component of enabling self-aware aerospace vehicles, and self-aware aerospace vehicles in turn are going to be an essential component that future of autonomous urban mobility that I talked about. So one of the problems that we've been thinking about is illustrated here, where you can imagine you have a UAV, an unmanned aerial vehicle, flying in some kind of an urban area. Maybe it's delivering packages. And while this vehicle is flying, maybe it undergoes some kind of an incident in its mission. Maybe it gets hit by something on the wing and it undergoes some damage. And so now imagine, you're an operator and you have thousands of these vehicles flying around. Clearly, it's not going to be humans monitoring the structural health or the battery health of these vehicles. It's going to need to be automated, and there's going to need to be autonomy so that the vehicle itself can make decisions. So we've been considering the case that this vehicle suffers this in-flight damage event. And then the question is, could you acquire data from the sensors on board the vehicle, on board the UAV, dynamically infer what's going on in the wing, so infer how damaged your wing might be, then dynamically update your structural models and issue predictions about, now, given your damaged state, how can you fly? What's your flight capability? And now that you have your new flight envelope, then dynamically replan your mission. And in the example you're seeing here, the UAV undergoes a damage event just right there in the beginning. And you can imagine it's got a very short amount of time to decide whether it's structurally able to take that sharp corner around the first building, that tight corner that follows the shortest path to the destination, or whether it can keep flying safely but can't pull the loads on that sharp corner, and so has to take the longer path around. And so again, you can imagine that with thousands of vehicles flying around in some future scenario, we're going to need digital twins for all of these vehicles with this kind of dynamic updating to ensure that the vehicle can fly safely. Next slide, please. Here's a second example. This is an example drawn from one of the concepts that the US Air Force is exploring, which is the idea of an attritable vehicle. So what we see here in this picture is an expensive and exquisite asset that is accompanied by these attritable vehicles. What does attritable mean? It means it's a vehicle that's kind of made cheaply and is not maintained necessarily at high levels. So it's almost like a disposable or a throwaway vehicle. And why would you do this? Well, again, if we start to think about the full life cycle of our vehicle, and we know how long the life cycle is of aircraft, all the way from the concept to disposal is decades, that maybe if you measure life cycle costs, it doesn't make sense to design, especially an unmanned vehicle, to design it so that it's going to withstand for decades. Maybe you can actually reduce life cycle costs by designing, manufacturing, and maintaining more cheaply, and then just kind of disposing of the vehicle earlier and getting a new one when the time comes. And that would be enabled also by rapid manufacturing. So, for example, with additive manufacturing. And it also would be enabled if this vehicle was operating as part of a team. So again, you can imagine that a digital twin is going to be absolutely essential for deploying vehicles like this, because you're going to need to know just what the vehicles are capable of as they start to suffer degradation over their life cycle. And you're also going to need to know when it's time to retire them. Next slide, please. And then the third example, or the third and fourth example, one of the things that I find so exciting about a digital twin is that even though it has its roots in aerospace engineering, and I talked about the history from the Apollo program, and also the fact that the term was coined by NASA, and the digital twin technology is really being pushed forward by aerospace, it's now outside of aerospace engineering into other parts of engineering, and then even outside of engineering. So in the news, you hear people talking about digital twins of all kinds of things, of buildings, digital twins of the planet to drive climate change, digital twins of people, or in this example here shown on the right, digital twin of a heart to drive towards patient-specific medicine. And while the physics and the underlying models are different, you can see sort of a lot of analogies in what I've been talking about within any of these systems of wanting to dynamically update models, collect data from the system, dynamically update the model, track as the Antarctic ice sheet changes its state, or as your heart changes its state, track that changing state and use that to drive better decisions. So again, really exciting to think about how digital twin technology might impact many things in the world around us, including our own health. Next slide, please. All right, so digital twins are really exciting. I think it's very easy when you talk about digital twins to get focused on the data. And obviously the data are a big part of it. I talked in the beginning about the technologies that enable the data and how those combine with the algorithms and the computing power to make something like a digital twin possible. But it's really important that we don't forget about the models. If we're going to create digital twins of aircraft and then use those digital twins to make decisions that relate to safety or to operation over an urban area, then obviously we have to trust the predictions that our models are making, that our digital twin is making. And prediction is a really important word in that sentence, because black box learning from data, so traditional machine learning, might be really good about inferring what's going on now, so drawing insights from the data we have, but that doesn't mean we have a model that will predict what happens in the future. And if you think about all the examples I've given, and we can think about that damaged aircraft having to decide whether it should take the short path or take the long path, it has to make that decision based on predictions of what would happen if I pulled a turn with this turn radius, what loads would I encounter, and then how would my structure respond. You're not going to get that from a model that you learned from data when you were flying straight and level. You need to have a physics-based predictive model. And, again, this is something that we as engineers think about as digital twins move into development, and as a lot of computer scientists and people outside of engineering get involved. I think it's really, really important that we remind people that it's the data and the models working together, and only then will we get a predictive digital twin that has the reliability and the robustness that we as engineers demand from our systems. Okay, next slide, please. All right, so that's just a few thoughts, and I'm going to tie back to them because I really wanted to sort of lay some context for some of the challenges and some of the opportunities that I think we're going to see or we are already seeing in aerospace engineering over the coming decade. And so now, as I move to talking about aerospace education, we're really thinking about, what does it mean to be an aerospace engineer? What should an aerospace education look like so that it prepares you for that kind of future that I've been describing in the digital age? Next slide, please. All right, so aerospace engineering has always drawn on multiple disciplines, and I know there are a lot of students on the line today, and I think you all appreciate this very well, because if you look back over all the classes you took as an undergraduate and maybe as a graduate student as well, there's so many different disciplines. So the traditional disciplines of fluids, structures, controls, propulsion, then of course, the more applied classes with aerodynamics, aircraft, spacecraft, design playing a really big role, the supporting areas of math and computing and physics, the experimental techniques. So already aerospace engineering, I think, is a very, very multidisciplinary domain, and the degrees have been very multidisciplinary. And already, even back when I was a student, almost 25 years ago, even then it was a challenge to try to fit everything into the curriculum, because we always felt like, the students need more aerodynamics, or the students need more structures and materials, or the students need more control, or students always need more design. So we go to the next slide, please. So aerospace engineering has always been multidisciplinary, and there's always been too much to try to learn in a degree. And now it seems to to be getting even worse, because there's really a need to cram more and more into your aerospace engineering education. So we can take everything that has traditionally been an aerospace degree, and then maybe many of you are thinking, well, you know, I really should take a class in machine learning because machine learning seems to be everywhere. Maybe some of you have been thinking I should take a class in neuroscience, and you know, maybe cognitive sciences, how the human brain works and how that relates to human decision making. Maybe many of you are thinking you need more classes in computing. So I'm sure you're already learning programming, but there are many other aspects to computing. So thinking about high performance computing, maybe learning how to program on GPUs. You know, again, many different skills in computing that you might feel like you need. And of course, all of these things are important, but I wanted to touch on a few thoughts about what skills will best prepare you for an interdisciplinary future, because as you plan out your studies, of course, you have to make choices and you can't do everything. Go to the next slide, please. So again, I want to share a few thoughts on that. First is, I think it can be really overwhelming. And again, you have to make tough decisions. My own students have to make these tough decisions. Should they take a class in machine learning, or should they take a class that furthers their aerospace engineering, more traditional disciplines? So the first thing is seemingly disparate topics share many common fundamentals. And this has long been an interest of mine, which is that even though we break the curriculum up into little pieces, and each piece is often very isolated and doesn't necessarily connect to other classes, there are so many connections among the different topics that we teach. And I guess I don't know how all of you really learn, but I find that I learn something best when I can look at it from many different perspectives. And I love it when I'll be sitting in one class or in one talk and I'll be hearing about something that maybe is related to fluids, and I'll think, oh, wow, that's really similar, or that idea shows up in controls or in structures. So when you see the same ideas showing up in different disciplines and different settings, I feel like that's a really valuable way to learn and to really to advance your very deep understanding of topics. So one of the things that I have worked on over the years is trying to understand this and trying to model it. So modeling how educational topics and pieces of a curriculum connect together. So I've worked on a few projects. You can find them at mapping.mit.edu. Projects that really look at in more granular detail what is being taught in classes and how those more granular topics connect to each other. And one thing that, you know, again, maybe it's obvious, but really comes out is that linear algebra is so key. Linear algebra shows up everywhere. And, you know, I think I would always tell my students at MIT, I'm like, take an extra class in linear algebra, take an extra class in linear algebra. And I used to say this before machine learning was a very hot topic. But think about where linear algebra sits. It sits in control theory. So it's absolutely essential, the concepts for controls. It plays a critical role in optimization methods. It's absolutely the backbone of machine learning. It's the backbone of solvers and physics-based models. So if you're working in CFD or finite element methods. And so it just is one of those fundamentals that sits everywhere. And again, going back to the earlier point, I think it's the case that seemingly disparate areas, so all those different topics I just mentioned, there are common threads that run through them. And I think being able to really have strong fundamentals and be able to make those connections is a way to really build a good foundation. Because at the end of the day, you're not going to be able to take all the classes you want while you're in school. And so really what you need to do is build your fundamentals and prepare yourself to be able to learn on your own in the future. Okay, next slide, please. So what does that sort of mean for how you might think about education? So the first point I've already made, having strong fundamentals is really essential. And, historically, I think engineering programs have had strong fundamentals in physics. So the fundamentals that underlie fluids and aerodynamics and structures and thermodynamics and so on. I think it's become increasingly important that you also have strong fundamentals in math and computing. And again, to come back to the earlier point, those three things don't necessarily need to be disparate. There are things like linear algebra that actually run across many of the follow-on classes. The second one is engineering classes teach you critical thinking. Don't underestimate its importance. So I guess I don't know, I should have asked Diego this before we started talking. I don't know what the situation is in Brazil, but in the US, there are so many students wanting to take computer science majors. And engineering is still very strong, but computer science just is growing and growing and growing. And there's a sort of a perception, or there's a thought among students that computer science is one of the most valuable degrees that you can have. And for sure, computer science is a valuable degree right now. But engineering classes teach you critical thinking. They teach you problem solving in a way that's, I think, quite unique, that's different to other disciplines. So as engineers, what do we learn? We learn how to look at a system, how to model it, how to think about what governing equations, what physical principles are there that would tell us something about the behavior of the system. We learn how to translate those physical principles into models, those models that we can either maybe solve with approximations and things like dimensional analysis, analytical solutions, but also solve using sophisticated computational models. Then engineering teaches us to look at the results that come out of the models and question them and ask about assumptions and to think about, just what we could say about what the system might do under different conditions. And then engineering really teaches us to put all that with design. So it's not just about understanding what's going on. It's about thinking. It's again back to those what ifs. And those critical thinking skills, I think, are so incredibly valuable and are skills that translate whether you stay in engineering or move into other domains. They're skills that really translate into very, very, very valuable assets. And I hear this from many people, that even if they're hiring and they're outside of engineering, that they really like to hire engineers because of those critical thinking and problem solving skills. So as you're deciding, whether to throw in an extra machine learning or artificial intelligence class, or you to throw in another engineering design class, don't underestimate the importance of critical thinking. It'll last you long in your career. And then the third point there is design experiences. And again, I already touched on this a little bit, but I think design experiences are so valuable in many dimensions. So not just related to the problem solving I talked about, but also thinking about how to bring disparate topics together, to do multidisciplinary integration, thinking about how to work as a team, experiencing the real world challenges of the data being noisy, the data not being enough, the models being wrong or imperfect, dealing with uncertainty, all those things, because those are all things that you're going to experience again and again and again in your career. So design experiences are so valuable, and things like this SAE competition, again, are just giving such incredible experience that I think is very valuable. So those 3 points are, of course, generically applicable. But I would say, and of course I'm biased, that aerospace engineering is probably the area of engineering that really does these 3 things, I think, very, very well and historically. So again, I started by saying there's never been a more exciting time to be an aerospace engineer because of what's going on in aerospace engineering. I think also there's never been a more valuable time to be an aerospace engineer because of all the challenges the world is facing and the world needing the kinds of skills that you get as an aerospace engineer. All right, next slide, please. All right, so let's just close by thinking a little bit about the future. So it's very clear that the future is very interdisciplinary. And again, I'm sure that you see this already, that maybe in the past, maybe decades ago, there was a strong need for more disciplinary engineers where people would be very expert in fluids or in structures or in materials and would be very, very focused. And of course, we still need those disciplinary experts, but the need to be interdisciplinary, to be able to stretch outside of your core discipline, to be able to deal with multidisciplinary challenges, it's already a huge need, and it's going to become even more so in the future. Now, when I say interdisciplinary, I don't just mean the technical disciplines. I don't just mean fluids and structures and controls and propulsion. It's already important and will be increasingly important to also be able to work across socio and economic challenges. So really integrating the technical considerations with the social considerations and then with economic considerations. And again, if you think all the way back to those first examples I was giving, none of those examples are problems that are purely technical, right? All of those problems have huge impact on society, whether it's landing humans on the moon or whether it's having autonomous vehicles flying around and interacting in an urban area. The impact on society, thinking about the impact on people, thinking about the impact on economics, they're all huge. So interdisciplinary means much more than just the technical disciplines. Second, I already mentioned teamwork, and again, I think you're already starting to experience this. But certainly people like Diego can tell you that teamwork is a huge, huge part of the profession these days. And teamwork is not easy. And I'm sure that often you feel that, you would rather work alone. I have an 11-year-old son who doesn't understand why he has to work in teams, because he tells me, Mummy, I can do it faster on my own. And sometimes it may feel that way, but teamwork is just an incredibly important aspect, because there is no way that that we're going to be able to solve those problems as individuals. Those problems really require teams. Third is versatility and problem solving. So who knows what the world will look like even next year. I don't think any of us expected to be in the situation we're in now. And while I've talked a lot about a vision for the future, recognizing that the future is so uncertain, and that we as aerospace engineers or whatever career we follow need to be versatile, because we might find ourselves in unexpected, both positive and negative situations. So versatility is really, really important. And then the last piece there, I think if there's one very good thing to come out of this pandemic, it's that the barriers to online education have really fallen. When I was at MIT, I was very involved in online education. I did a lot of work, particularly with MIT's OpenCourseWare. And while we were doing a lot with online education, there was still a lot of resistance to doing more. There was a lot of resistance to having parts of the MIT degree be online. And I think in the past year, because we've had to do it, we've recognized that even though face-to-face education is and will be incredibly important, there are parts of the education that we can do online. And with that barrier dropping, it's now such a huge opportunity, because it means that you can be anywhere in the world. You can be in New Zealand, you can be in Brazil, you can be in the US, and you can start to access new kinds of education. Second, a lot of what I've talked about is that you need to know so much. You need to acquire so many skills, and there's just not time to do it. So you can really start to think about your education as lasting through your entire life, and using virtual education as a way to enable that. So again, if there's one really good thing to come out of this pandemic, I'm optimistic that it is going to change the face of education in our work environments in a positive way that lets us all be lifelong learners, where we can really access education from anywhere. All right, next slide, please. So that's, I'm going to stop there. If you're interested to know a little bit more about some of the projects I talked about in the beginning, you can check out my website there. But other than that, I'm going to turn back to Diego, and I would love to hear any questions or any thoughts from you on these topics. Thank you.
Thank you very much, Karen. In fact, your presentation was fantastic, very inspiring. And yeah, actually, before going into the questions we have, I would like to ask one myself. Because I saw that during your presentation, you showed an image of a neural network, and you talked also about predictive models. And sometimes we have a bit of resistance, especially in the industry and especially in the civilian aircraft industry, with regards to reliability and safety. And neural networks, because they are kind of a black box, some people are a bit afraid of using it. So I'd like to ask you, in your experience, if you had that kind of resistance too, and how to overcome that.
That's a great question. So, Diego, I have to be honest with you and tell you that I am one of the people resisting the neural networks. So, I mean, obviously, you know, neural network modeling is incredibly powerful and has achieved remarkable results in a number of settings, particularly in the computer science world, you know, for image recognition, natural language processing. And so, you know, I don't debate their power, but, you know, I think engineering systems are different. You know, as I said in the talk, we demand different things from our models. That first of all, we ask our models not to explain what they've seen, not just to explain what they've seen, but to predict the future. And as engineers, by definition, we issue predictions about conditions that we've never seen and that we never want to see. So, right, we have to design a system to ensure that it doesn't fail. And we wanted to simulate either on the computer or in experiments those failure conditions that we never really, you know, want the system to get into. So being predictive, and then you mentioned reliability. You know, 10 to the minus 9, 1 in a billion. Well, you know, if a neural network can get you a 1% accuracy, that's not going to help you with 1 in a billion. So I think the hesitation is justified, but of course that's not to say that this kind of modeling, neural networks, but also other kinds of machine learning models may not. It's not to say that it can't be useful in other ways. So, for example, in my group, some of what we work on are multi-fidelity methods, where we say a surrogate model, which might be a neural network. We tend to use Gaussian processors, but it could be a neural network. A surrogate that you don't know how good it is. In fact, you know it's approximate. You wouldn't rely entirely on it, but it can be useful together with a higher fidelity model in accelerating the computations. So I think that way of thinking that, you know, neural networks are not going to, in my view, are not going to replace everything else we do, but they could become another toolbox in our engineers' toolbox that lets us design more quickly or you know, explore more scenarios. So that is the way I would think about it. But I do worry a little bit that there's so much excitement over neural networks that people lose sight of what it is we ask our models to do, which is a lot.
Thank you. Thanks for the answer. And yeah, now I'm going to go through the questions the audience had placed. The first one, the most voted one, is: do you think that more multidisciplinary classes in universities could help make greater engineers in the future?
Yeah, that's a great question, and you know, it's so hard. It's so hard, and we often, you know, at MIT would debate this, which is it good to take a design class early on, right in your first year, when you don't have the fundamentals, but you can bring the different disciplines together and kind of learn just enough to be able to take on something multidisciplinary? Or is it that you really need to see the foundations? You need to see, foundational classes in fluids and structures and controls and propulsion and physics and math, and then at the end have the integrative experience where you start to think about multidisciplinary. And I think the answer is you need both. Both are valuable. That when you're in the multidisciplinary setting, you start to see those sort of connections among the disciplines, which gives you, like I was saying, a different perspective. But then you absolutely do need the foundations too. I don't think we can replace all of our classes with multidisciplinary. So I think we have to have a balance. And again, I think so much of the value that I've seen the students get comes not through their classes, but through this kind of SAE competition. These things that you do outside, whether it's design, build, fly, or it's your own project, or it's a student club like the Rocket Club, or a competition, that's really where the huge value comes. And so having organizations like SAE and AIAA creating those kinds of opportunities for students, I think, is really, really, really important.
Yeah, great, thanks. And it turns out that the second most voted questions is also about MDO. So because that's something that's quite a challenge in the projects, in the competition. So people are very interested in that. And the question is, do you think that digital twins can be integrated with MDO to feed a big database to improve even more the design optimization of aircrafts?
Yes, I do. So there's digital twins, and then there's a related concept of digital thread. So, a digital twin being kind of, like I was saying, the asset-specific model that's going to follow this aircraft through its life. And then digital thread, which is closely related, the idea of connecting data across the full life cycle. And I think those two working together really can impact. So in the examples I gave, I talked a lot about operation, but can really impact the way we design vehicles. And they can impact in many ways. So the first way is, if you were designing an aircraft and you knew it was going to have its digital twin, so you were designing not just the physical vehicle, but you're also designing the digital twin, you might make different design decisions, right? Because you would think more intentionally about the sensing capability. And especially, for example, with the structural health, thinking about how the digital twin can help with the structural health management, as opposed to maintenance on a time schedule. But that might lead you to make different design decisions, because the trade-offs are going to be different. So I think that's one way. A second way is when you have digital twins, and then when you have this digital thread that integrates things, you have the opportunity to learn, right? You have your products that are out there that are in operation, or that are through the manufacturing. So it becomes a more systematic way to start to feed back learning and thinking about whether there are ways you can change the design for your next generation of systems. Now that's hard for large commercial aircraft, because design gets locked in so early. But if you're thinking about smaller, and especially UAV type design, where the design turnaround times are more rapid and things can evolve a little bit more rapidly, I think there are huge opportunities there. So absolutely, I think digital twins can play a role. The question used the term database, and the database is going to be a really big part of it. But again, don't forget about the models, right? The models that sit in there under the MDO process. But yeah, I think this is great. And can we do that today? Absolutely not. But this is a really exciting area of research, is how to bring all this, how to bring this together.
Great, thanks a lot. The next one, I admire your work, and I would like to know if you have advice for anyone who wants to become a professor and researcher in aerospace.
Yes, so, well, thank you. Well, I can first tell you, I never expected to become a professor. Actually, I came to the US to study aerospace engineering because I wanted to be an astronaut, and I don't know if that's the reason for many people choosing aerospace engineering. And even when I finished my PhD, I was applying for jobs in industry, and I did not imagine becoming a professor. So I think my first piece of advice is you have to be open-minded, because you never know what opportunities might come up, and how you might like something that you never sort of imagined yourself doing. That's one piece. Again, I mean, even to the first interview I had for a professor position, I was saying, well, I really don't want to be a professor, and the advice was just take the interview and keep an open mind. And now, 20 years later, I am still a professor. So being open-minded. Second is mentors. Mentors are so incredibly important, and I think of everything I've managed to achieve in my career, and none of it, absolutely none of it, would have been possible without the incredible people that I had mentor me. And that started, in school, and then through undergraduate mentoring to help get to the US. And now, even now that I'm senior in my career, I have incredible mentors who give me advice. Sometimes the advice I don't take, but just, sort of thinking about other people's experiences and perspectives, and mentors who've just helped with little opportunities sort of along the way. So I'd really encourage you to think about who your mentors are. And if you don't have good mentors, then maybe try to be a little bit more proactive in seeking them out. And they can be your professors, they can be, people in your workplace, they can be, just people in the community. And again, that's where the professional organizations like SAE and ARAA play a huge role, because that's what makes you sort of a part of the community, and to start building your networks. And then maybe third is just do what you love. Sometimes you have to do things because you feel you have to do them, but you should really follow your passions, because if you are passionate about something, you're far more likely to do it well. And I can tell you, over my career, there have been many times where people have told me not to work on a certain project. So for example, the educational work that I mentioned, I got told multiple times to stop working on it because I needed to focus on other things. And I was like, you know what, this is something I'm very passionate about. I care about education. I'm going to do this. So I made my own choice. And, I think, again, ultimately, if you're passionate about something, you're going to do it well. And that is more important than trying to be too strategic and planning out the things you think you should do because you think somebody else thinks you should do them. That's not the reason to do
it. Sorry, Karen, I think we lost your audio.
Oh, I can you hear me now?
Now I can hear you, yes.
Okay.
So that was great advice indeed. When you do what you love, it's much easier to reach the goals. We have a few more questions here. Let me see. Is it possible to use digital twin to feed the real-time semi-autonomous control of a small UAV with complex maneuvers such as EPJS and very sensible to wind? That question was from Gustavo.
So is it possible now? I don't think we're quite there yet. Will it be possible in the future? Yes, I think so. What is it going to take? It's going to take a lot of integration of data and models and the onboard software. It's going to take surrogate models. So Diego asked earlier about neural networks. Here's a place where you're going to need powerful models that have been trained in an offline phase but can execute really rapidly online. And it may be that this is where things like neural networks and other surrogate models play a big role. So there's, I think, still a lot of research and development that needs to be done. But I believe, yes, I think with the algorithms and the computing power that we're starting to see, and things like the neuromorphic chips that are starting to again mature, the kind of computations we might be able to do on board the aircraft with low weight and low power consumption really open up new possibilities. So I'm optimistic that we will see those kinds of computations on board vehicles. I guess one key question will be, can we make it cheap enough? But I suppose historically we first get it right technically, and then later on the technologies become cheaper.
Okay, great, thank you. Next one. Okay. As a student, how can I encourage multidisciplinary integration in my institution to improve my graduation? That's a nice one.
Yeah, that's a good question. You know, if your institution's already not that way, it can be very hard to get universities to change. Universities change very slowly, very, very slowly. But I would say the thing to do is to complement what your university does with your outside activities. So start a student group, start a student club, and try to get your institution to support you to do that. So get involved in Design, Build, Fly, or one of the rocket competitions, or start a local chapter of SAE or AAA, or whatever the professional organization is in your area, and try to get your institution to support that. That would be my advice, without knowing where you are and what the situation is.
Yeah, okay. Next one, how can a student enhance this interdisciplinary connection through individual study time? I'm very inspired, amazing presentation.
So, I guess everybody has it's hard to sort of say this is the way to do it, because there are many paths and it'll be different for everybody. But again, get good fundamentals. Use your time at the university to get really good fundamentals in math and physics and computing. Because once you have good foundations, it's like building a building. When you have good foundations, it's easy. It's going to be better to build on top of that. And then you have incredible resources with things like OpenCourseWare and edX, and all the free online classes that are available. So I think once you have your foundations, you can do a lot of self-learning with other classes. And don't feel like you have to rush to do it all now while you're students, because your career will be long and you'll be able to acquire new skills once you get into the workforce. So really focus on your foundations and teach yourself how to learn. Find friends who have common interests. Put together study groups.
Great. Next one. Thank you for the presentation. It is a very relevant subject. I'd like to know how we can apply for master's and doctoral degrees with you as advisor.
Well, maybe that's something to take offline. I mean, you can send me an email. I have a big group at the moment, and so I'm not taking on too many students, but there's always future times. So send me an email.
Okay, good. There's one is just a remark. Karen, for me as a woman and future engineer, it is inspiring to see your work. Thank you very much.
Great, thank you.
And a last question. I think this one might have been done by one of the members of the committee. I would like to invite you to participate in the competition when the pandemic is over. I believe that many of the aspects you brought, our design encourages us.
Absolutely. I think we're all looking forward to the pandemic being over so that we can do these kinds of things in person, which is so much better, because then we can meet each other and form those networks that I was talking about being so important. But absolutely, yes. I'll look forward to that, Diego.
For us as well. So yeah, that was all the questions we had. So yeah, we can thank you more for accepting our invitation and giving us this fantastic presentation. Thank you very, very much. As people said here, you inspire a lot of people, and congratulations for your work. And yeah,
great. Thank you. I can see my network connection is coming and going, but thank you very much, Diego.
Thanks a lot, Karen. Have a nice week.
Thank you. Thanks.
Bye-bye.